Okay, so can you guys see the slide again? So we were seeing the concept of convolution, and first thing that I showed was what is an impulse response, h of n. The second thing I showed was that any discrete time signal can be represented as sum of scaled delayed impulses. And then based on these two, you can say information, we can just build the theory of convolution, and that is what I'm building right here. So if you have any system, discrete time, and we give x of n, you get h of n, y of n as an output, it's an, and this is a discrete time LTIs. Now what we saw was that if we give delta n as an input, what comes out we call that as response h of n. And I was just trying to draw this here, that first of all, what is delta n? We know that delta n is basically a single input at n equal to 0. So if this single impulse is given, what comes out will depend on what type of system you have. We can have a very simple system where, let's say, a single impulse just scaled by out. This can be your h of n, which is typical for an amplifier system. The scaled version of that impulse comes out, so that is an impulse response. Interestingly, we may also come up with a system where we give a single impulse and a whole series of impulses. So 1, 2, and 3. So we end up getting more than one impulses out. So this may be your h of n. So your n, this is your n. Or not finite. So, or another interesting situation maybe you give a single impulse to it, and the output is not a single impulse but a whole series of impulses which are infinite in nature, and these impulses may be, let's say, decaying sort of a thing but continuing throughout, or these may be diverging sort of a thing. So we can have single or countable finite number of impulses, or we may have an infinite number of impulses. Based on this, we can categorize the response that we get as either a finite impulse response system, a system which as a result of single impulse gives us finite number of impulses as a response. So finite impulses response are there. That is one particular category of system. Or we may have another category of system which is known as IIR. This IIR part is actually your impulse response, and F is actually finite, or I means infinite. So depending on what type of system you have, you may have either a finite impulse response system or you may have a infinite impulse response system. Now these terminologies of FIR and IIR, you may have already heard it, but if you have not heard it, so you'll start hearing it from now onwards, and throughout your engineering career you will keep hearing these terms. It's an FIR system, it's an IIR system, the impulse response is this, system is stable, system is unstable. So these types of terminologies you will come across a lot later on once you become engineer. So we are introducing these terms here, although in your slide sets or in your book this may not be covered in detail, but in DSP these things, FIR and IIR, will be discussed in detail, that how do you come up with an FIR, how do you come up with an IIR, advantages of FIR, advantages of IIR, how do you make FIR, how you make an IIR. So these types of things you will see later on. But here, coming back to our original first theory, that is theory of convolution. So for convolution theory, we actually first of all covered two basic concepts. One concept was that of a impulse response h of n. The other concept was that of breaking up x of n in terms of sum of scale delayed impulses. Okay, so coming back to this, if we have an LTI system, delta n, a single impulse will give you h of n, impulse response. Because it is an LTI system, It has got property of linearity also and time invariance also. And linearity we know has two parts. One is the scaling part, the other is the additive part. So if we just scale it with any factor, the output will also get scaled by the same factor. And similarly, if we just give a delayed impulse to it, the output that we will get will be the delayed impulse response. And if we scale it by some factor, whatever factor it is, so the output will also get scaled by the same factor. And we can continue with this thing x to some scaling factor with some delay factor. If that is given as an input, the output would be the same scaling factor with delayed impulse response. And we can go on and on and on. Now, instead of giving individual signals, if we just give some of these signals as an input, so that your x of n is just sum of all these inputs, some scaling factor with delayed n minus k for all k, and k be from minus infinity to infinity. It can have a whole range of scaled impulses. The result that you will get would be y of n, which will be just sum of all these added together. And if you just sum that up, it would be sum of, again, a scaling factor, the same scaling factor, x of k, and impulse response is h of n minus k. So scaled delayed impulses will result in scaled delayed impulse responses, and multiple of scaled delayed impulses will give multiple of scaled delayed impulse responses. So this is what we are going to get. So this will be the output if we give an input of this shape. Now if you see this, this is a generic or generalized form of discrete time signal. So any discrete time signal can be broken up in shape of scaled delayed impulses. So if you give that as an input, the scaling factor, if we know, we can find out an impulse response. If we know, we can find out output for that discrete time signal. So this is what we get, and this summation that you see, x of k, h of n minus k, this summation, we call this summation as convolution sum. We call this as convolution sum. And we have a symbol for this also. At times we just write this y of n as x of n. We just give a symbol to it, convolved with h of n. So this star symbol is your symbol for convolution. Let's call it convolution symbol. So this is your convolution symbol, that star sign that you see. So this is that theory of convolution, that if we are given any input, all we need to know is the impulse response. If we know impulse response, then output would be just convolution of input signal with your impulse response. And what is that convolution? What is meant by convolution? Convolution is basically convolution sum of x of k, h of n minus k. So this is that theory. And this is something extra that we covered, that what's an FIR, what's an IAR. This is something which is technically not part of this course, it's part of DSP, but it's good to know. Okay, so let's see what slide actually talks about, and this is exactly what the slides are going to tell us, which I just scribbled in last about 1 or 2 pages. Okay, this here actually talks about the convolution. Convolution is an operator that takes input signal and returns output signal based on knowledge of system's impulse response h of n. And system impulse response is basically what system gives an output once we give an impulse to it. A unit impulse, if that is given as an input, the output that comes is your unit impulse response, or simply put impulse response. We just tend to call it impulse response h of n. So if h of n is known and x of n is known, we can find out output for any given discrete time input. So the basic idea behind convolution is to use system's response to simple input signals to calculate response to more complex signals. Now this is possible for LTI system. If you recall what we scribbled on just blanks just a few moments ago, the theory of convolution or convolution sum will be valid only if you have a LTI system, because LTI system possess that linearity property and time invariance property, and we can use the superposition property to come up with response. So typically what we have done, we can break down x of n in terms of sum of scaled simple signals, and the simple signals that we chose was basically your impulses, delayed impulses. So we know the response for impulses, it is impulse response. Scale sum of scale delayed impulses will give sum of scale delayed impulse responses, and that actually gave us our theory of convolution. Okay, so this is what is shown right here, although it is talking about the same thing here, that we can express any discrete time signal in terms of sum of scaled delayed impulses, and depending on what type of signal we may have impulses starting from 0 going all the way there, or we may have impulses on left hand side and right hand side both. So whatever we have, we can just express the signal in terms of scaling part and this delayed impulse or advanced impulse. So we can just add all these together and give you your signal, and this is what we actually showed, that any discrete time signal can be represented in terms of sum of scaled delayed impulses. So this is basically one property that we actually used, and here it is showing you an example, not a very good example because it actually talks about a situation where you have, this is your n equal to 0, so n equal to 1, 2, 3, 4, and n equal to -1, -2, -3, -4. We have values on both sides. So if you have that type of x of n, if this is your x of n, this can be broken up into individual impulses. The first impulse, and then the second impulse, the third impulse. So we can just take them as individual impulses, and if you add all these impulses together, you will get your original signal back. So any signal x of n can be decomposed into its individual additive components or individual impulses, which are basically scaled and shifted. Okay. Now, as I mentioned, a very important way to analyze a system is to study the output once we give unit impulse signal as an input. That is what we actually talked earlier. So if you want to find out the details about the system, that how the system will behave, all you need to know is how the system is going to respond to a unit impulse, and that unit impulse response or impulse response is good enough for us to judge how the system is going to behave, because using this h of n, then we can find out how the system is going to behave for any given input. So giving an impulse is like sort of giving a kick to a system and see what happens, that the output that comes out, is it a single impulse, it is more than one impulse or finite impulses, or a series of infinite series of impulses. So the symbol or notation given to impulse response is h of n, and it is used to denote the output signal if we give a unit impulse to it. And this output signal h of n is then used to find out or infer properties about the system structure, parameters, and its behavior. So here we have example of 3 different systems given. So this is example of 3 different systems, and it is showing you that what are the different types of impulse responses that can occur, and I showed you on that blank earlier also about this. So it is the same thing shown here. So this is one example, that if you give a single impulse delta n, the output that comes out, which is impulse response h of n, it can comprise of a finite number of impulses, just like shown right here. And example of one such system is right here. So this is basically one example. If this is your system, equation of system is given or difference equation is given. If you give a single impulse to it as an input, you will see that output that comes out would be a finite number of impulses, just 3 impulses. So that's why we call this as a finite impulse response system, or FIR. Another example is a system shown right here. And here we see that in this system, if you give a single input delta n to that system, you will see that the output that comes out, the system response h of n, would be an infinite number of impulses starting from n equal to 0 and going on and on and on. And it is basically your decaying sort of impulses, but infinite. It just goes on and on and on. So this is an example of a IIR, infinite impulse response system, IIR. And similarly, here is another example of a third system whose equation is given. And if you give a single impulse to it, you will see that we end up getting increasing or expanding values of your impulses, but infinite. It will go on and on and on. So this is also a infinite impulse response system, IIR. So 3 different examples of impulse responses are given for 3 different systems. And here, that thing that I showed on a blank slide shown right here also, that what the output will be depends on the system. And it all depends on the difference equation of the system, because this difference equation actually determines what type of system you're going to get, or what type of response you're going to get. Now, this is a very interesting thing that we can take from here. If you see this first one, this second one, and this third one, 3 equations are given, 3 difference equations defining 3 different systems. The first one is FIR, the other 2 are IIR. Now, can you just look at the system and find out whether it is an FIR or IIR? This is something which you will become expert of by the end of DSP. I keep repeating this, but most of the expertise you will gain by the time you finish your DSP. Here, the introduction is being given. Okay, so can we actually just look at the equation and find out whether it is an FIR, or can we say it is an FIR or IIR? The answer is yes. You will become expert of that, but this particular thing right now you can judge. How can we judge that? If you see this first equation, difference equation, to compute your output, we require delayed scaled inputs only. We require just a scale delayed x of n's. And because this scaling part is having just previous values, and the delaying part has previous value x of n minus 1, x minus 2, there is no x of n plus anything. So we know that this is going to be a causal system. Now, let's just leave that stability part, how we know it is stable. It will just come to that in a moment. But first come to FIR. How do we know? Because these are 3 properties we are listing here: causal, stable, and FIR. How do we know it is FIR? So you should know that if the output depends on present or previous inputs only, then you will end up getting an FIR. If output do not depend on any previous outputs, then we will have a FIR. You see here that to compute y of n, we require present and previous values of x only, or present and previous values of inputs only. X is at the input. We don't require any y of n minus any term. So there are no such y of n minus something term present here. So there are no previous outputs required to compute your present output. Or in other words, there is no feedback required. It is just feed forward. Now this feedback and feed forward, what does that actually mean? If you see the symbology that we use, x from this side, y from this side. So this is basically the path that is taken. So present or previous x are all coming from this side. So this is basically feed forward. If we use any previous y, we need to just take it back and add it right here. That will be fed back. So if you have just x's here, we say that we have all feed forward terms. If you have any of the y, then we say that we have a feedback term included also. So if you see here, so this is your y of n minus 1, previous output added to your previous output. So output with one delay will be added right here. So previous output added. This is your feedback term, a single feedback term being added to your feed forward term. So even if you have a single feedback term or single, in other words, y of n minus something term, you will end up getting an IAR. We can have more than one also, y of n minus 2, y of n minus 3, but even if a single y of n minus any term is present, then you will end up getting an IAR. Here another example, if you see here, again y of n minus 1 scaled to some value is added to your x of n. So this is the feedback term added to your feed forward terms. Here we have just feed forward terms. There is no feedback term involved. So if only feed forward terms are there, there is no feedback term, you will end up getting FIR. And if even a single one is present, it is IAR. If there is no n plus any term present, it will be causal. It will be causal. Now, how do we know this is stable or not? That thing will come later, but this one, you will see that all FIRs are stable. If it is an FIR having feed forward terms only, we can directly write it as stable. No matter how many terms we have, no matter how much scaling factor is included, it will always be stable. As a rule of thumb, if you have a feedback term and the scaling factor with feedback term is greater than 1, later on you will see, mostly that will end up resulting in unstable thing. If the scaling factor of feedback term is less than 1, you will end up getting stable. So if feedback scaling factor is more than 1, mostly you will end up getting unstable. But there are better ways to judge that. So IAR we need to be careful about. They may or may not be stable. FIR will always be stable. And that is why FIRs are preferred, or terms having the difference equation having feed forward terms are preferred. Those systems are preferred because they are always stable. So most of these terms are not relevant to this course, but because they are included on the slide, I just explained that. This again in detail you will cover FIR and IAR part specially. You will cover in your DSP, but it was just to give you an idea. So this is just this slide. The main take home message here is that your impulse response may comprise of a finite number of impulses, or it may comprise of infinite number of impulses. If you give a single impulse, as an input, the output that comes out, it is not necessary that it will be just one impulse or finite number of impulses. It may be infinite number of impulses. So there are two categories of system. One is those systems whose impulse response is finite. The other is those systems whose impulse response are infinite set of impulses. Okay. Then coming back to your theory of convolution as we were covering. Now, this terminology that you see right here, this is old terminology. We're not going to use this terminology. So this HKN is terminology which is used for shifted h of n. The more commonly used or more recent terminology is this. This is how we represent shifted h of n. h of n delayed by k units. So this HKN also means the same, but this terminology is old. These slides are taken from second edition, which is an old book. Third, fourth, fifth edition, or fourth edition is out, fifth is still not out. So those actually don't prefer this terminology. Or recent books written after, let's say, year 2004-5, you will see that this terminology is used for the shifting part. Okay, so if h of n minus k denotes response to the shifted impulse delta n minus k, because it is this shifted impulse, then we can actually use the superposition property of linear systems, and then we can first of all write x of n as sum of scaled delayed impulses. This is something we have seen at the beginning, that we can represent any discrete time signal in shape of sum of scaled delayed impulses. So any x of n can be represented as sum of scale delayed impulses, and because of that we can also come up with a, you can say, notation for output for any discrete time signal. If this is x of n, y of n would be this, and this is basically system output, which will be sum of scale delayed impulse responses, and we are not going to use this, we are going to use this convention x of n minus k. And this summation convention is what we call as the convolution sum. It is sum of scale delayed impulse responses. So sum of scale delayed impulses result in sum of scale delayed impulse responses. And sum of scale delayed impulse responses is also known as convolution sum. So this is not a very good example which is covered, but I will come to that in a few moments. So this is basically showing you that hk can be written as h of n minus k, and this is the most commonly used convolution sum notation. So convolution sum for LTI system is given by this. This is more common notation used. And we have a symbol for this, and this symbol is that star symbol. So this arrangement is known as convolution of sum. It is called as the convolution sum. It is also known as superposition sum, although this is hardly used. This term is hardly used. We typically refer to it as convolution sum because it actually involves convolution of two signals x of n and h of n, and we have a symbology for that. It is written in this shape: x of n convolved with x of n, h of n, and this convolution actually means convolution sum. Okay, this is as far as the theory part is concerned. So now let us first take a simple example. So can we actually, if we know impulse response and we know input signal, can we find out the output? So we know that for discrete time, x of n is the input and y of n is the output. So if we have given h of n, can we find out the output if we have a LTI discrete time system? So that remains to be seen. So let's take a few examples and see that how this theory can help us find output for any given input if we are given x of n and h of n. So let's say you are given x of n, which is 1, 0, 2. This is x of n given, and let's say our h of n is also given to us. H of n is given to us as, let's take a simple example of let's say 1, 1. So if input is 1, 0, 2 and we know that our system impulse response is 1, 1, then can we find out the output y of n? Can we find out output y of n using this convolution theory? Now to solve this, there are basically 2 or 3 methods. First, we can just use the simple graphical method or ab initio initial method of finding the output. And for that, what we need to see is delta n going to give us h of n, right? And this actually, x of n is having delta n and it is having a 0, and then it is having a delta n minus 2 scaled by 2. This is delta n. This is delta n minus 1 scaled by 0. I have not mentioned it here. This is delta n minus 2 scaled by factor 2 or multiplied by 2. So if we have this plus this plus this, so this plus 0 plus this, then what should be the output? If input is this, what should be output? Delta n gives you h of n. 2 times delta n minus 2 will give you 2 times h of n minus 2. And this plus this, if that is given as an input, this plus this should be the output. Now what is this plus this? First of all, we know that h of n is given to us. It is just 1 and 1. So what is 2 times h of n minus 1? So if h of n is 1 and 1, what should be h of n minus 1 or h of n minus 2? Let's just take h of n minus 1 first. It should be h of n shifted right by 1 unit. So if this was, let's say, this, and this 0 and 1 having 1 here, then this should be shifted right by 1 unit. This and this at 1 and 2. This should be h of n minus 1. How should we write it? It should be just 0, 1 and 1. Similarly, if it is h of n minus 2, it should be shifted further right, and you should have first 0 and then 0 and then 1 and then 1 and scaled by 2. So if we have to add these two together, so let me draw that here also. So this is your h of n minus 2. This should be 0, 0, 1 and 1. So it should start from here and here. Start from 2 and 3. Okay, so if we have to add these two together, what should we get? This was, if we take 2 inside, it will become 0, 0, 2 and 2. And this should become 1, 1, 2 and 2. So your x of n, which we just add these two together, is basically delta n plus 2 times delta n minus 2. The output y of n is basically this. Either we can write it as this, or we can plot it, or we can just write it as delta n plus delta n minus 1 plus 2 times delta n minus 2 plus 2 times delta n minus 3. So either we can write it as this or write it as this. Right? So this is one example of doing or solving if we are given x of n, we are given h of n. So we will see that how this thing can be done. Okay, so now let's take another view of the same thing. We know that y of n is basically convolution of x of n with h of n. And we know that convolution actually means convolution sum, summation of k equal to minus infinity to infinity, x of k, h of n minus k. Remember, this x of k is the scaling part that we have. This is your y of n. So this was the theory that we covered. Instead of going for that whole graphical method that you see here, instead of going for the whole graphical method, we can just limit ourselves to mathematical equation and solve the whole thing. So y of n is convolution sum. Now, what are the limits? Minus infinity to infinity. Now we cannot have an infinite number of terms. That actually, the limits actually are dictated by this particular scaling factor, x of k. Now k can be 0, 1, 2, 3. So if you see here, we have value for x of 0, we have value for x of 1 and x of 2. We don't have values for all the negative parts of k or all the values of k greater than 3. So we have values for 0, 1 and 2. We don't have values further here or further there. So x of k exists for k equal to 0, 1 and 2. Or in other words, the limits should be starting from k equal to 0 till 2. X of k, h of n minus k. Right? So if we just open this up, this y of n summation, if you open up, this actually becomes x of 0 and h of n minus 0, which is h of n, plus x of 1, which is 0 below, h of n minus 1, plus x of 2, h of n minus 2. Right? This x of 1 is 0, we know, and this value is 1, this value is 2. So we just write it as 1 times h of n, and h of n was 1 times h of n, which is 1 and 1, plus, let's write it here. So the x of 2 part is 2 and h of n minus 2 is 0, 0, 1 and 1. So if we just write it again, it will end up becoming 1, 1 plus the second part becomes 0, 0, 2 and 2. So if you just add them together, we end up getting 1, 1, 2 and 2. This will be your y of n. So either we can just directly use the summation or we can use the graphical part. We end up getting the same answer. We end up getting the same answer that you see here. Any confusions here? A simple, you can say, example shown where we found out what the output would be if we are given the input discrete time signal and if we are given the impulse response of the system. Any questions here? Any confusions? No questions? So this example which is shown is a bit more complex because here x of n is given as 0, 0, 1, 1.5000. You see, this is not a very good way of expressing x of n. This becomes clear only once we plot it right here. If you see here, this is your n equal to 0 part. So x of n value exists for n equal to 0 and n equal to minus 1. And this is for n equal to 0 and n equal to, sorry, this was minus 1, n equal to minus 1 and n equal to, let me just try to erase this. So as I mentioned, this is not a very correct way of expressing your x of n because this creates confusion. Where is this 0? What is that? Sorry, question? Is there a question there? Okay. So the confusion comes that what is the index part here? There is no indication that this should start from n equal to 0 or n equal to what? Although in diagram we can see that it is starting from n equal to minus 3. This index is shown right here at minus 3. So how do we know this is minus 3? It is only through the graphical representation that we came to know. But from the written part itself, if somebody writes this, that x of n is equal to, let's say, minus 1 and 1.5. So what is that index here and what is the index here? What is the index here? What is the index there? This is something which needs clarification. So in this example shown, this is not covered right. So if there is no indication, no qualifying statement, no diagram, nothing, then the first index is always 0, n equal to 0. But as in this case, if first index was supposed to be something other than 0, then there are two ways to represent it. One, an old way, the other more recent way. I will show you both ways. First way, old way, was that whatever is the starting value index, that index is written right here under here. So I will just write minus 1 right here. This minus 1 written in the square bracket actually shows that the index or the location of the first value is at n equal to minus 1 and the other one will be at n equal to 0. Likewise, this is at n equal to minus 3, a minus 3 will be written right here. This was the old convention. More recent convention is that instead of writing an index right here under the square bracket, we just put an arrowhead identifying the location of n equal to 0. So in this case, n equal to 0 exists right here. A simple arrowhead will be used right here, and all the recent books written after year 2000 or some older ones also use this convention, but all the latest ones, the recent ones, actually use this convention. If you are following this course from any of this American site or European site, you will see that this arrowhead will be actually used to represent the 0 location. In this case, your arrowhead will be right here. In this case, right here. So this is actually arrowhead showing you the location of your 0. If there is no indication, then if I have to write this, if there is no indication, then the assumption would be that the first index is at n equal to 0. The first value would be at n equal to 0. So this is something which needs clarification, and in this slide actually it is not covered rightly. I believe in the book also it is kind of not very clearly mentioned if you are following the second edition. If you're following fourth edition onwards, you will see that arrowhead and all that type of thing. Okay, so again, if x of n is given, and again this convention I don't like, and this is again an old convention, and h of n minus 1 or h of n, how do we actually represent this? So if we are given h of let's say, okay, I'm just not covered this example because not very nicely written. Let me give you example on my own. So more common example that you will be seeing will be something like this. Let's say 0.5, 1 and 0.5 with an arrowhead right here, and let's say h of n given to you as, okay, so how should I do this? Let's take a simple example of 1 and 0.5, nothing given. So if you have to find out y of n, then again this is summation. Now k equal to minus infinity to infinity. Let me write the whole thing first. X of k, h of n minus k. So this is your convolution sum, and in this case x of k value start from -1 and ends at 1. So I will just write it as k equal to -1 to 1 x of k h of n minus k, and then I'm going to just plug in the values. This will become x of -1 h of n plus 1 plus x of 0 h of n minus 0, which is h of n, plus x of 1 h of n minus 1. So this is again, this is x of -1, which is 0.5, and h of n is this. H of n plus 1 will be this shifted left by 1 unit. So this will be your same 1 and 0.5, but if it is shifted left, that means the first index will be -1 and arrowhead will come right here, plus x of 0, which will be 1 into 1 and 0.5 and arrowhead, although we don't require it, but let me put the arrowhead, plus x of 1, which is 0.5, and h of n minus 1, which is shifted right by 1 unit. So this will be 0, 1 and 0.5. Although we don't require it, but you can put it right here. So we can just add all of them up and find the answer. So if we just first of all write everything as it is, 0.5, 0.25 plus the second part, which will be, again we have to align the arrows. This arrow was here, this arrow will come right here, 0.5, and the last part would be again 0, 0 and 0. This is your arrowhead right here, and this will be 0.5 and 0.25. Is that right? No, that's wrong. This will be 0.5, this will be 0.25. Okay, that's right now. And arrowhead is going to come right here. Okay, so this is a bit more, you can say, complex or involved example, and if you just add all of them together, you will end up getting 0.5, 1.25, 1 and 0.25, and the arrowhead location right here. So once we are adding these types of things together, you notice that the first one I just wrote it as such. The second one, just to align the arrow, I need to put a 0 right here. So, and I need to put all the arrowheads together so that they are aligned. Only then we can actually add. So diagrammatically, what actually we were doing right here. So this was, let's say, 0.5 and 0.25. So it was basically 0.5 here and 0.25 here. So this was the first term. The second term that we had was starting from 0, it had 1 right here, and the second part was 0.5. And the third part was where we had 0 first, and then we had 1, and then we had 0.5. It was just adding these terms together. So if we had to add all these terms together, we had to align this axis. So it was 0.25 here, 1 here, so 1.25 coming right here. So it was basically zeros and zeros here, and 0.5 here, so 0.5 coming right here. And this was, let's say, 1.5, was it? Or am I wrong somewhere? Okay, I was wrong here. This was 0.5, 0.25. Okay, this is 0.5 and this is 0.25. Now it's right. So if we have to add these two together, this will be 1, and if this is added, this is here. So this is your y-value. So we can either graphically draw them and add them, or we can just align all these zeros together and done. Now this confusion or problem will come if you have this type of situation where x of n or h of n values are on the left hand side also. Then we end up getting this alignment issues. If that thing is not there, then the thing becomes very, very simple. Like the example we saw where both x and h starts from n equal to 0 and there is no term on the left hand side, and the convolution also became very, very simple. Any confusion, any questions here? So this is basically your convolution and some examples of convolution. Now, so there are other examples which, and first of all, system identification and prediction. Note that system's response to any arbitrary input signal is completely determined by its impulse response, by the response of that system to a unit impulse. So if we need to identify how a particular LTI system behaves, all we need to do is to apply a simple unit impulse signal and measure the system response. So in other words, all we need to do is give delta n as an input and find out what is h of n. So once we have found out h of n, then that h of n, that data can be used to find out or predict the system's response to any input signal. This is what we have shown in last few slides in this particular lecture, that if you want to find out how the system is going to behave for any given input, all you need to do is you need to find out its impulse response. You need to find out its h of n. And once you have found out h of n, then that can be used to find out the system output for any given input signal. So this h of n holds that it completely describes or defines your system. Note that describing an LTI system using h of n is equivalent to description using difference equation. Now here we are saying that if you know h of n, we can find out output for any given input. But the same statement we gave once we described your difference equation, because the very definition of difference equation was that it gives you relationship between input and output, that how the system responds for different inputs. We can just give the value of x of n in your this difference equation and find out the output. And the example is shown right here. So this we saw earlier also once we saw three different systems. This is a system having your feed forward terms only in your difference equation, and this is going to be an FIR system. So There is a direct mapping or direct relationship between h of n and your difference equation, especially if you are having an FIR. So why do we say this? So if you have this thing given to you, y of n is equal to, I'll take another simple example. Let's say x of n plus 0.5 x of n minus 1 plus 0.25 x of n minus 2. So if this is a difference equation given to you, we know that this is going to be a FIR. So this is one equation which completely defines your system, and the properties of the system are this: in FIR, it's a causal system, and because it is an FIR, we know that all FIRs are stable, so it's a stable system also. And because it is having n minus something term, it is a memory system also. So there are so many terms that we can use. So many properties just by looking at the equation. It's a FIR, it's a causal system, it's a memory system. Now, this equation completely defines your system. For any given input, we can find out output. For any x of n, we can find out y of n. So whatever x of n is given, just add it here and you will find out your output. The other thing we saw was that if we know how the system responds to your impulse or impulse response, that completely defines your system also. Now there is a direct relationship between h of n and your difference equation. How, why, and especially for FIR, It will not be so true for IIRs. So if you are having an FIR, from the difference equation we can find out your impulse response. How can we do that? So if x of n is an input, y of n is an output. If instead of x of n we have delta n as an input, if input is delta n, instead of x of n we have delta n. Instead of x of n minus 1 we have delta n minus 1. Instead of x of n minus 2 we have delta n minus 2. So if instead of x we replace input x with delta n in the difference equation, the output that we get is called h of n. So this is your h of n. From difference equation directly we got difference equation, and either we can write it like this or we can write it like this: 1.5, 0.25, or we can just diagrammatically draw this h of n as 1.5 and 0.25. This is 0, 1 and 2. So three different ways in which you can represent your this. So there is a direct relationship between the difference equation and impulse response. Both of them are one and the same thing, and there is a direct mapping. We can directly find out h of n from y of n, especially if you have having a FIR. Now this type of thing is not possible if you are having a IIR. Why is that? Because for IIR you are not having feed forward terms only, you are having feedback. At least one feedback term will be there. Example, we saw multiple examples, but just take an example like this. Okay, plus, okay, x of n plus 0.7 y of n minus 1. This is again a difference equation. Now instead of x of n, if we replace delta n, y becomes h of n. This becomes h of n is equal to, this will be your delta n plus 0.7 h of n minus 1. So we end up getting h of n minus 1 and h of n. H of n itself is what that has to be extracted from this type of equation. So we cannot directly find h of n from difference equation, just like we can do for FIR. For IIR, we can't really do this. Although, if we can have a very simple way of solving it, we can find out h of n. But right now, take it from me that This direct mapping is easily done for FIR. If it is an IER which is having a feedback term, then there is no simple method or direct method of finding h of n from difference equation. So this is another thing that needs clarification. Although in this slide set, it just says that we can directly find out, but I have just qualified it that we can directly find out in case of FIR, just like we have here. So in this, replace x with delta and you will end up getting your h of n. So this is another example where we are doing convolution, where we are given h of n and we are given x of n. So I will not solve this here, so you can just take it. You can just take it from here onwards. So we'll be going to cover this in the next lecture. So up till now, any questions?